Yeah, is the recording on? No? Sangita, is the recording on?
Yes, yes.
Okay, then it's fine. So let me just give me a minute. Yeah, so I talked of the postulate 5, which is the for any arbitrary psi, the following time-dependent Schrodinger equation holds A psi st. So now for the first time, am I audible? Hello,
Yes, sir.
can you see the screen also, right?
Yes, sir.
So for the first time, we are discussing how the wave function changes with time, and so to that extent, we are bringing in the time, and we again said the importance of the Hamiltonian, that the Hamiltonian, uh, that is there. Just a minute. Just a minute. Yeah, so this is the time derivative is kind of controlled by the action of the Hamiltonian. So that is what we said, and that is why the Hamiltonian plays a very important role. Now, every arbitrary psi satisfies this, and this is called time-dependent Schrodinger equation. However, the other Schrodinger equation, A psi equal to E psi, is a time-independent Schrodinger equation, uh, which is controlled by the equation A psi equal to E psi. So that is very, very important to realize that this is not generally true. This is only a condition for stationary. That is something that I mentioned. Now, those which satisfies this also satisfy this. So of course, a psi which satisfies both of them would be an interesting thing to note. So basically, because we are interested in the stationary states, we would like to know what is the time dependence of the stationary states. So that is very, very important. So that is what we will do. And then general time dependence of a property for any state, how does it evolve, will be actually talked about in the Ehrenfest theorem. So that is what I want to discuss. There will be a quiz for about 30 minutes on Thursday. I think that has not changed, right? Yeah, so there will be a quiz on 30 minutes for Thursday. The rest of the 30 minutes, I will complete my classes. So today and the Thursday, I will complete the Ehrenfest theorem, and I will hand over for the applications of H psi equal to E psi for particle in a box and so on. Okay. All right. So let me see now. So let me go over. Hello. I'm not able to get that mail immediately. I'm already in a class. It's very difficult. Can you ask Simran? She is in the teaching. She is today TA. No. अभी कैसे हमने क्लास ले रहा है? अच्छा, नहीं ऐसा क्लास I told you. Yeah. Just talk to Simran, not yeah. No. You text her. Yeah. She'll send. Yeah, I'm sorry about too many phone calls coming. Tough, bad life. All right. So we have the time-dependent Schrodinger equation, which is given for arbitrary size. So that's a part of the postulates of quantum mechanics. We have called it postulate 5, but the postulate 3 was very long. Hello, Simran, can you send the link to Madam? See, and just call her and tell. Maybe have some. All right. So now what we are saying is that this psi is a function of x. Again, it's a one-dimensional problem, except that I've introduced time as a new variable. And this also satisfies the time-independent Schrodinger equation. So that is our constraint. So let us say that I write this psi xt as a function of x and a function of time. So that's the standard way of doing, because position and time can be separated. Our positions are not time dependent in the sense that position is changing with time, but the variables are not coupled with each other. So I can separate this. This is usually called a separation of variables, and this is a condition that works in the case that we have separation of dimensions. Okay, and there is no particular part in the Hamiltonian which is coupling this position and time. So we can actually separate these and then write this same Schrodinger equation as the Hamiltonian acting on phi x of time part equal to IH cross del psi del t. And now you know that del psi del t will act only on the time. So it will become dt dt with the phi of x as a constant. Right? So for a general psi which can be variable separated, we can write in the following manner. This is a general psi. Now we are saying that this psi is also a stationary state of Hamiltonian, which means our condition is that the position part, phi of x, is an eigenfunction of the Hamiltonian, with an eigenvalue which is energy. So this is an additional constraint. This constraint is a condition. This is coming from the condition of stationarity. So then, if I substitute this here, you get an equation which is IH cross dt dt phi of x, and now I will write h of phi of x as e of phi of x time. So you can see that I have simplified the equation. Now the Hamiltonian is over. Hamiltonian action has been taken care by the fact that it is equal to the energy times phi of x, because we are looking at stationary states. So we are now looking at only stationary states of energy. All right. This was the general equation for any arbitrary psi. Then we can come to a very simple part. We can write down a first order differential equation for the time part alone. That is, how is the time part t of t changing with time? By eliminating phi of x. So how do you eliminate phi of x? That's a very important question. So I multiply this equation on the left hand side as well as on the right hand side by phi star of x and integrate over all x. The rest will remain as it is. IH cross. So this is the integral. IH cross dtd. I do the same thing on the right hand side. So I have e of t integral phi star of x. Please see this very carefully, what I'm doing. I multiplied both left and the right hand side by a phi star of x. And now I'm integrating this equation over the x. So right now I have time and x. So I wanted to get a time part separately. So how do you get time part separately? Remove the position. How do you remove the position? By integration. It's very simple. All integrals are definite integrals. I do the same thing here, and clearly whatever is the value here is the same as this. These are all normalizable functions, so this is not infinity at least. Whether it is normalized or not is unimportant. They are identical, and then I land into a very simple equation of the time part alone. Time part is given as capital T, E of time. So this is a function of time, this is a function. I hope it is clear to all this exercise. Please do not cancel this like this. Huh? There are sometimes even textbooks suggest just cancel this. You can't do that.
So it may be 0 at some points, the phi of x.
So you can't do that. You can't do that.
Okay.
That's what I'm trying to tell. So you cannot take inverse of a function like that in general. Otherwise, I could multiply by 1 by phi x and cancel. But the inverse may not exist. What exists is the normalizability. Okay. So at a particular point, because you really don't know what is the value, but in a way you can argue that the normalizability will eventually make this non-singular, and hence the inverse exists, hence I can do 1 by phi of x. But I think this is a much cleaner way of doing it. That simply multiply by phi star x, you have to only integrate the variables. Okay. So you get a simplified equation. This is a standard first order differential equation, which you must have done. I'm not writing partial derivative because this is now only one variable. Here I had written del because there are two variables, position and time. Okay, so I had written position. You should always use partial variable because position can be many, although I am using as an exemplar only one dimensional problem, but there can be many position variables. But time, of course, is one. So I can just solve. So can everybody know how to solve this?
Yes, sir.
Hello? Yes, all of you know. So what do? You bring time here and you write this as a dt of t by t of t. So you simply divide by this part, IH cross equal to E. Okay, and then integrate. And then further you integrate. And get the t of t, and this is easy to show that it is e to the minus I e t over h cross. The minus will come naturally when you do that exercise. Then we divide by I, which has got up and then become minus. Okay. So this is a time part that is of great interest to us. If you now see the time part, it is exponential minus I e t over h cross. So at any point of time, when I do psi star x t psi for any variable, for a stationary state, and this is an important point to note, for a stationary state, the psi star x t psi x t is time independent. I hope you can understand this. Because you have e to the plus IET as a star of this, e to the minus IET here, they will cancel, right? So there will be no time. And this is very important to realize. That means the probability for a stationary state only, because I have used the fact that the h phi equal to e phi. So I can say for a stationary state, the probability function are time independent, right? Not only probability function, any average value. You talked of average value. If this is a stationary state of Hamiltonian, it may not be a stationary state for another operator. Then we said How do you get an average value of an operator? You will simply do psi star A psi, right? Now that there's a time, if this has no time, but this has a time, only wave function. But remember, I'm explicitly saying that this has no time. Variable is time independent, operator is time independent. Only the time comes from the psi, then these are also time independent. For the same reason, because the time part only has here, and they cancel each other, psi star psi. Is it clear? So all observables, average values are also time independent, and not to mention that the energy is time independent. This is all true for a stationary state. However, if it is not a stationary state, then it is much more complicated. Further, if the Hamiltonian has a time, then also it becomes complicated. So we will worry about those classes because there are different types of physics. Many times the Hamiltonian contains time-dependent part. Then, of course, it is not so simple. But in such a case, you will not have a stationarity here. So for all stationary equations, for a time-independent Hamiltonian, which is what we will focus on, whole of quantum chemistry, the time is not a factor. I want to again repeat this because we'll do particle in a box, harmonic oscillator, hydrogen atom. Many times you'll ask the question, what happens to the time? I want to make a blanket statement. The time is something that I can forget. After today's class and the Thursday's class, we'll forget about the time. For all stationary states, because our attention will be on stationary states for this part of the course. But as far as quantum physics is concerned, time is important, of course. And those are things which happen for scattering, resonance states, and so on. Spectroscopy. You have to understand time because you have a time-dependent external field. How does the system respond to that? So I think it is very, very important that the time cannot be completely ignored. But for the part of chemistry, the quantum chemistry or the electronic structure, what we call, the time at this point is not important for the entire class. So I could actually, that's why I said the postulate 5 is important. You must know, but you must know that eventually it doesn't matter. Despite this postulate, it doesn't matter if it is a stationary state. Is this clear? And this kind of time factor is called the stationary state time factors are called phase factor of time. This is called a phase, which simply cancels out when you take complex conjugate. And that comes from the first order differential equation. With that, we formally close the postulates of quantum mechanics. And I repeat some of them. The postulate 1 spoke of a function for any given state, a function which should have certain desirable property, and one of the most important desirable properties is that it must be normalizable, it must be continuous, it has to be single valued. You can also have one somewhat desirable property is a derivative continuity. But certainly the most important part is the normalizability. Okay. Then we said that the psi star psi as a function of x, we did not discuss time at that point, is a probability density of finding the particle at a point x. Then we went to the postulate 2, where we defined the dynamical observables. Any dynamical observables are represented by an operator which is Hermitian. I hope you had some discussion on the Hermitian operators, and the important part is that the Hermitian operator has real eigenvalues. Hermitian operator has eigenfunctions which can be so constituted to form a complete orthonormal set. Complete is very important, as well as orthonormal set. If two such operators commute, they have simultaneous eigenfunctions. So some of these we have not proved, but we just made a statement on postulate 2. In postulate 3, we said that now we are going to put these two postulate 1 and 2 together and say what happens to the measurement. So we said if psi is any arbitrary function, which is not an eigenfunction of that operator, then if you make a measurement, you will get different values but all those different values will be one of the eigenvalues of that operator. You always get the eigenvalues of that operator. So that was what we said. And in that case, what we can do is to define an average value. So to define the average value, there is a Copenhagen interpretation that the arbitrary state can be written in terms of an eigenfunctions of that operator. The coefficient square, mod square, is the probability of getting that particular eigenvalue. That's an interpretation. Using this, we wrote an average, which turned out to be psi star A psi. So this postulate is often separated into two postulates. One just saying that they get real eigenvalues, another is average value, the interpretation. 3 and 4 doesn't matter. We present it as one postulate. And then the final postulate, then the next postulate was, if it is a stationary state, then I always get the same value. So that's like classical thing. There are lots of stationary states. We specifically mentioned the stationary states of energy, which is H psi equal T psi. Finally, we looked at the time-dependent Schrodinger equation for any arbitrary state as a final postulate. And we said that if this is a stationary state, the time part is trivial. If it is not a stationary state, yeah, it is not trivial. Okay? So this is what we said. I wanted to come back to that discussion that if I have a Gedanke experiment, what I discussed in postulate 3, if I make an arbitrary measurement, then of course we will get a different value. So let's say that A of phi I is lambda I phi I. And this is an arbitrary state psi. Then we can only find out the probability of lambda I by the following stricture, that psi can be written as sum over Ci phi I. I hope you're following this, because this is a complete orthonormal set. This is an orthonormal set. And each of the coefficient can also be obtained by a scalar product of the corresponding phi k, kth coefficient, with this state psi. This is in Dirac notation, but it is simply written as phi k star, whatever is the position variable, psi x dx. So I can get each function ck, and then my probability of lambda I, of getting a lambda I, is nothing but mod Ci squared. So that was the Copenhagen interpretation. Please don't forget that. And then the average of any operator, the operator that I'm measuring, is nothing but sum over Ci squared.
Sir?
Yes.
Sir, I have a question that when we are actually measuring this Ci, before
we are not
that,
measuring Ci. We are not measuring Ci. We are only measuring this value.
Yes. I mean, when we are
This is an
calculating,
interpretation.
yes,
This is a calculation. Yes.
Before that, we must have normalized the wave function.
No, normalize. It has to be normalizable. Okay, I mean you can say normalized. It doesn't matter. That is a very minor point. This is a complete orthonormal set.
Yes, sir. But if we have not normalized, then the probability of, I mean, ck mod square, it
Of course.
will not be less than 1. I mean,
Yeah, then you can normalize it. So
okay.
yeah, I mean, of course, I would. Yeah, that point is a trivial point. I mean, these are all normalized probabilities.
Okay, sir. Okay, thank you.
Yeah, please do not get worried about normalized. Normalized can be always done if I have not done it. So you are right that I have been talking of this as the probability provided psi is normalized. That is what you are trying to say. That my Copenhagen interpretation, this is probability assuming psi is normalized. Is that what you are saying?
Yes, sir. Yes.
Yes, sir. That is correct. That is correct. Yeah, but that is really beside the point, because if it is not normalized, I can normalize it and recompute the coefficient. Everything will be just multiplied by 1 by square root n. Okay. So yeah, I mean, if that point has to be stated, I must state it, that this probability, I assume a normalized wave function, and then get the coefficient, then this is the probability, then I can calculate the average. This suggests a very complicated procedure, because for every dynamical observable, I must get its eigenvalues. I must expand eigenvalues and eigenfunctions, sorry. I must find out this. For every dynamical observable is different. And then I have to calculate the probability. So it's a very complicated thing. But what it turns out is that the entire thing can be written as simply psi star A psi. So this is much simpler. You have the dynamical observables. Of course, you have to do for every dynamical observable an integration, but only one integration. Here, imagine how many integrations you have to do for each of them, and then some. And of course, each of them you cannot do because this is infinity. So this is not a procedure, I'm repeating, this is not a procedure, this is not a practical procedure to calculate the average value. This was stated as an interpretation. The practical procedure comes when I mapped this to this and I showed this, how this is equal to this, if you remember, right? Or I actually showed the other way around. From here I can go to this, but doesn't matter. Having showed this, this is practical evaluation. Just one integration. I don't need to know all the dirty things about that dynamical observable. This is very, very important. I'm repeating this part because this is the heart of the Copenhagen quantum mechanics. The other important part was that once I make a measurement, initially I get a probability. So let's say this person gets lambda 1, this gets lambda 2, this gets lambda 3, this gets lambda 1, and so on. Lambda 2 and so on. So if I have only 5 here, you can see the lambda 1 comes twice, lambda 2 comes twice, lambda 3 comes 1. So the probability of 1 is 1 by 5, lambda 2 is 2 by 5, this is 1 by 5. Right? I mean, that says simple probability of 5. Of course, this is not correct. You require infinite number of measurements. That's a different matter. What I'm now trying to say is a very, very innocent statement that Dirac made in his book. It says that every dynamical observable, and this is where there is a metaphysics, which I did not discuss, every dynamical observable is immediately repeatable. Every dynamical observable is immediately repeatable. Now, this is a very difficult point. It was a very innocent statement, and it required a lots of discussion, and the discussion went in the realm of metaphysics. What do you mean by immediately? Now, immediately is, first of all, a vague term, imprecise term. It meant that the time gap should be 0 between two measurements, and assuming that the time is not an important thing, yes, time gap is 0. But what it essentially meant is the following. And actually, with the time-dependent postulate, you can argue that this psi is not an observable, it's not a stationary state of the A, so time also should matter. So what it actually said is the following. Let's say this guy gets lambda 1. This robot, he makes a measurement of A, R1, the robot R1, gets lambda 1. What it said is that if this robot 1, initially we did not know who will get what because there is only a probability. It is not clear that the robot 1 would get lambda 1. The robot 1 could have got lambda 2. But if the robot 1 gets lambda 1, this statement was interpreted in the following manner, that if the robot 1 makes an immediate measurement on the same system, the robot 1 will continue to get lambda 1. Do you understand? If the robot 2 had got lambda 2, continue to get lambda 2. If robot 3 had got lambda 1, again, will continue to get lambda 1.
Sir?
Yes, yes.
I mean, sir, is this statement, is equivalent to the term that the wave function collapse?
Yes, absolutely. So, yes, I'm coming to that. So, when there is a big discussion, they said, look, what happens is the following, that as soon as there is a measurement, the psi changes. You get an observable lambda 1, so the psi will immediately change. The psi has changed to phi 1, which is an eigenfunction of the operator A corresponding to lambda 1. In this case, the psi has changed to phi 2. This case, psi has changed to phi 1, depending on the robot. Now, the point is, Einstein was very, very upset because you, first of all, don't know which robot will get what. You can't predict. And then once robot gets something, it just changes. So it is completely unpredictable. They said, yes, up to this point is unpredictable. There is only a probability. I could not predict that the robot 1 will get lambda 1. But after robot 1 gets lambda 1, the state has now changed to phi 1. And now it's a stationary state of A. Don't forget, my phi I are eigenfunctions of A with eigenvalue lambda I. So it said that this operator has an eigenvalue and eigenfunction. If you get lambda I, it will change to phi I. And because it is now an eigenfunction of the lambda of the operator A, it is not a wonder by the postulate that I mentioned or the condition that they will get to continue to get the same value, right? It's now a stationary state. So the damage was done in the initial observation. Initial observation, it changed the eigenstate, what you are calling collapse. Okay? So it changed the state to phi I, phi 1, but in a way that is completely unpredictable. You understand? Because I didn't know which robot will get what to begin with. So I will get phi I, and then it will just get locked into phi I. Lambda I will get locked into phi I. So this is a very difficult interpretation. I hope you understand. This was a rather difficult interpretation. Yes.
Sir,
Yes.
okay, Anish, you ask first.
Sir, so after suppose R1 gets the wave function as as a eigenstate, then the wave function will evolve in time as per the time evolution factor. Or will
Yes,
there
because now it's a stationary state, right? Of
okay.
A. Stationary state of A. But remember, it is not stationary state of Hamiltonian. So, but it's a stationary state of A. I will now come to the Ehrenfest theorem to show that if it is stationary state of A, it is still time independent. I will show that little later. The stationary state has I have already shown that if it is Hamiltonian stationary state, the time is a phase factor. But you will now see what happens. If this operator is time independent, that is something I'm assuming. So I'm assuming that the operator A itself is time independent.
Sir, I have a question. That, sir, I mean, you said that after the robot 1 measures the system, he gets the eigenvalue lambda 1. And then after that, whenever he repeats his measurement, he still get lambda 1.
Yeah, lambda 1.
So, I mean, did his act of measurement
Yes,
force the
yes.
system to be
Right.
in lambda
No,
1 state,
right,
or was
right.
it in lambda 1 state?
It has changed. No, it has not changed. Originally, it was not there, obviously. So the act of measurement, that is important. Act of measurement changed the state. But in a way that you cannot predict. You could not have predicted a priori. Changes the state in a way that it was difficult to predict a priori. How it will change? Only thing that I knew, it will change to, sorry. The only thing that I know that it will change to one of the eigenfunctions of the operator. But which one will change to which eigenfunction, I had no clue. Till the robot gave me the value. Once robot said, I got lambda 1, now I know it is locked into phi 1. So this change of this state, and this is a very difficult thing to understand. That first of all, I don't understand how it will change. It will change. And this change depends on which robot is measuring. This one is giving lambda 1, this one is getting lambda 2. Actually, robots are not doing any experimental error. The system is changing naturally. So then people started talking of subject-object interaction. That is there an interaction between the subject and the object which changes, and the changes in a manner which is difficult to predict.
Sir, do you mean difficult to predict or impossible to predict?
It is impossible to predict. That is right, a priori. That's important. Now, difficult is a difficult part to say, because if psi is such that the probability of 1 lambda I is 0.99, you understand? then I would probably be able to predict in most cases. If it is already stationary state of A, then of course the issue does not come, because that becomes the postulate 4.
Okay.
I talked of Hamiltonian specifically, but for all operator it is same. If it is eigenfunction of this operator, then everybody will get same value, everything will remain same. It's not interesting, it's boring. You understand? As a physicist, as a metaphysicist, it's boring. There's nothing interesting about it. The original state itself was phi 1, phi 1, phi 1, every gate is phi 1, lambda 1, and it will continue to be even phi 1. It's boring. No change with time. As long as time does not change it. As long as you do not perturb it by time-dependent external field and all that, nothing will happen. But in this case, if it is non-stationary state, then subject-object interaction is very important. And provided the probability is not heavily loaded, it's almost impossible to predict by guess. If it is heavily loaded, your guess may be right. That is what I mean to say difficult. But yeah, technically speaking, it's impossible to predict. Precise prediction, you can say it is impossible. The precise prediction with any precision, scientific precision.
So,
But
sir, I just had
yes.
a general question that, I mean, for momentum and position, you had defined, I mean, for momentum, you just said the operator is multiplied by x, and for momentum, it is differentiate, I mean, partial differentiate with del by del x and multiply by h by I, h cross by I. But for any other kind of dynamical observable, which, I mean, we don't know what the operator is. I just wanted to ask.
We know. I'm sorry. Postulate 2, I said that every classical observable, A classical, can be written in position of momentum. And from this construct, I can get quantum mechanical operator.
Okay, sir.
I think I did that for kinetic energy.
Yes, sir. Yes. But sir, my question was something like, I mean, we have the system in front of us, and we know a way of measuring the whatever observable we have. I mean, we have some instrument which is measuring, so we can know the quote unquote eigenvalues which the system is giving. So just from those eigenvalues, can we reconstruct the operator and the wave function? I mean, knowing those eigenvalues.
You can do that, yeah. But that's very difficult. What you are saying that I will give you all lambda is construct the operator A.
Yes, and psi.
That's very difficult, I would say. Construct psi. I mean, in principle, probably it is possible. If you know lambda I and phi I, I have understood your question. But the fact is that the postulate says that the psi is already given. So why do you want to construct? You can test the postulate. Okay. So you can say that I will do a thought experiment and then test the postulate. Right? By giving you lambda and phi I, now find out. But I can say these tests are really, if you want to test the postulate, you can do that, but it's not necessary. You are given psi, you are given A. Both of them are given. That is the reason I said the average value is psi star S I, right? It's very easy to do that. Correct? So these two are anyway given. I think this is a discussion that those who are interested, we can do later. Okay? What I will now do is to just make this statement of the Ehrenfest theorem and close. So I'll have a discussion on the Ehrenfest theorem. However, Ehrenfest theorem will be outside the quiz. Ehrenfest theorem talks much about the time, and the time that we are discussing will all be contained. There are tremendous consequences of Ehrenfest theorem. So let there be an operator A, and Ehrenfest theorem is very general. So I am also allowing the operator to be time dependent. Though in most cases, the operator will be time independent. But when I'm writing the Ehrenfest theorem, I will have an operator which is time dependent. It can have external electric field and magnetic field, so it can be time dependent. I have an arbitrary psi, which is a function of position. Again, for the simplicity, I'm still continuing with the one-dimensional problem and time. This is an arbitrary psi. This is an arbitrary operator. So anything. There is no relation between the A and psi. Eigenfunction, no such relation. then I know how to calculate average value of A, right? Don't forget that the average value of A is psi star xt, A of t, psi of xt, dx. If I only write integrate over the position coordinate, then this is an average value is also time dependent, right? I'm not integrating over time. At a given time, I integrate over coordinates. So the average value of time dependent. Now, what does the Ehrenfest theorem do is the following, that it gives you how does this average value change with time. So I'm going to write this as d dt. I hope you understand average value of A. I can write d dt because time is only lone variable. And the Ehrenfest theorem says this is equal to d dt, sorry. It is the average value. I hope whenever I'm writing average value, you understand what it is. The operator, psi star and psi left and the right, integrated over x. So it is the average value of del A del t. This is the partial variable of A with time. It's also an operator. Average value is psi star on left, psi on the right, integrate over dx. Plus 1 over IH cross, the average value of an operator which is the commutator of A with H. Please note that anywhere I'm writing this symbol, it means psi star and psi integrated. It's an average value. I hope that symbol is not going to confuse. So for example, my symbol of del A del T is nothing but psi star xt del A del T. That's an operator. Psi xt dx. Integration is over x. Same thing here. Integration is not over time. So this is the time derivative of the average value of A. This is a very general statement which was first stated by Ehrenfest. In all our examples and the cases, this is usually 0. So this is 0 provided our A is time independent. And I think we are mostly discussing such cases. So in all such cases, the only thing that will really remain is this part. That the average value of the operator A, which is now time independent, with that operator H, which can be also time independent, average value of this, which is the most of the case that we are discussing, because we are not really worried about time with respect to psi star psi, and that is the part that will govern the total average value derivative. And this is there, but this is the Ehrenfest theorem in generality. What is written in red, what I marked out in the black, is what survives for the time independent operator. Is it clear? I will prove this theorem. I just stated it. Okay, so I will prove the Ehrenfest theorem. I think we have to also look at the proof of the two operator commuting operators having simultaneous eigenfunction and a Hermitian operator having real orthonormal, complete real orthonormal basis. We will see how, obviously I cannot do that in half an hour on Thursday, because there will be a quiz first, and then so I will first complete those two theorems. We'll see for a teaching tutorial at a given point in tutorial. We can do that. Maybe one of the Tuesdays I can come in and finish that.
Sorry?
Okay. Yes.
Sir, first of all, will the quiz be MCQ or descriptive questions will be there?
I don't know. Professor Sen is there. Has he discussed it already?
Ma'am has told that the quiz is about 20 minutes and all questions are MCQ.
Oh, then it's fine. Then it will be MCQ. Professor Sen, are you there? Hello? Is he there? Can you see? Yeah. So what we are saying is that I think what he said, the madam has told that it will be MCQ, multiple choice question. Okay. So we'll stick to that. No problem. Is there a question? Any problem with that?
No, sir.
Yeah. MCQ for 20 minutes. Okay. All right. So MCQ is MCQ, and at this point we'll probably stick to one correct answer. There are different types of MCQs. I hope you know. Sometimes there are multiple correct choices, multiple options are correct. How many you do correctly, it depends on that. But at this point of time, we will do only single up correct option. So it's
Sir,
much easier. Yeah.
Sir, can you please increase the time by 5 or 10 minutes? It will be very helpful
But
because there are
how many questions you will give?
20.
20 questions.
Yes,
No, I
ma'am.
think she meant 20 minutes.
I don't know. She
Yeah,
said just
that I'll
MC.
discuss. That I'll discuss. No, we'll be reasonable. I also feel 20 questions, 20 minutes is not reasonable.
Okay.
So,
Okay, sir. Thank you.
yeah, I will try to change that. But she's not here right now. But I will. But I don't think she meant it. She's probably said MCQ 20 minutes.
Yes.
How many questions? That will depend also on the question. How much you can think, right?
Yes.
And I have not said the questions right yet. So
Okay.
there is no question of saying this. So I will have to think over. So we'll see. The reason that 20 minutes because that 10-minute turnover, and this will be right at 5 o'clock, right?
Yes.
Yeah. So after that, the class will start. So there will be a little bit turnover. So I need at least half an hour to prove the Ehrenfest theorem and its consequences. That is very important. I'll write them down. Proving is easy, but consequences are something that I have to write down. And then I will discuss the rest of the operator algebra at some other tutorial, some other day. I will hand over from next Tuesday. Next Tuesday to Professor Sen. I'll come back later in another Tuesday to finish it. And of course, I'll come back later, even later again. It's not that she's going to conduct the whole course. Right? For the next part, she will do, and I will again come back later.
Sir, the
Any
Tuesday
questions?
the syllabus will be till today. The portions.
Till today, except the Ehrenfest theorem.
Okay. And for midsem, including reference theorem.
Yeah, then midsem will include Ehrenfest theorem, of course. When is the midsem? Next week, right?
Yeah, next week.
Yeah. So midsem will include everything. So not
Okay.
next week. I said next week Professor Sen will start. Yeah, then of course this is a very natural time to break it. So before the particle box starts. So yeah, we'll have basic quantum mechanics. The first part, the failure of classical mechanics, black body radiation, Einstein photoelectric effect, hydrogen atom, and then we'll have the basic framework of quantum mechanics in the midsem. Okay, and we will discuss the midsem on Thursday. I will first discuss with her, and then I will tell you what the midsem format will be. Okay.
Okay, sir.
Okay. Thank you very much. Close the class now. Okay. Thank you. We'll see you on Tuesday first for the quiz. So please come attend the quiz part. 5 o'clock, please come, and then for the continue with the class. Okay. Bye.